Hello once again, and welcome back to our ongoing look at analytic trigonometry, which is a bit of a mouthful, but as we're seeing, it's a relatively tame idea. It's just looking at sines and cosines, not from its roots, not rooted in unit circle or right triangle stuff, but just for their own sake. And previously, we've been looking at identities, equations that are always true. We've found quite a few such identities, and we've used them in very many different ways. Some ways included finding exact values of some esoteric expressions. We've used them to prove new identities and show that equations have always equality. They're always satisfied no matter what values we put into those equations. So now the time has come for us to take a step away from that, because not every equation in the universe is always true, right? Something like sine squared x plus cosine squared x equals to 1, yeah, that's an identity. That's always true. And that's because it's a Pythagorean identity. But some of the other equations we have looked at, the question was, okay, I have an equation. I know it's an identity. That's the answer, right? The answer is yes, it is an identity. The question is, how do I show it is an identity? How do I show that my equation is always true? And we've looked at simplifying, substituting, other identities, other formulas, and those were all the methods we used to show that one expression on the left is equal to the other expression on the right all the time. Well, that's no longer going to be the case. Think about not sine squared plus cosine squared, but just simply sine squared x equals 1. Now, previously, we were trying to show that something was an identity. This is clearly not. In fact, we could have shown that simply this is not an identity just by picking pretty much any number. Take x to be 0, sine of 0 is 0, that squares to be 0. 0 is not equal to 1. You take x to be pi over 4. That would show it's not an identity. Take x to be pi over 3 or pi over 6 or negative 17 pi over 4. You know, anything really except maybe for pi over 2. Sine of pi over 2 is 1, that squares to be 1. So that would be a solution. So recognizing it's not always true, the question becomes, when is it true? When is sine squared x equal to 1? It's not always, but when is it? And we'll come back around to that. I want us to start off thinking about some specific questions. For what values of theta is it going to be the case that sine of that theta angle is equal to a half? When is it the case that cosine of an angle is equal to a half? When is it the case that tangent of an angle is equal to a half? Right, we can get specific solutions using inverse trig. Right, we can do the arc sine to both sides of that first equation, and we will get a solution, because arc sine will undo sine, as long as we're on the specific interval from negative pi over 2 to positive pi over 2. And we will get an angle on that interval satisfying this equation. Right? Pi over 6 is what we would get if we did the arc sine of a half. It's what our calculator would give us if we were in radians mode. If we were in degree mode, it would be 30 degrees. And that would be a solution. Doing similar for cosine via arc cosine, we would find a solution to cosine theta equaling a half to be pi over 3, or 60 degrees. Doing it again with arc tangent, that's not going to be a nice thing. We'll end up getting 0.4636 in radians, or 26.57 degrees. And we'll get a solution using our inverse trig for each of these equations. But there's no way that's all of the solutions. That can't possibly be all of the solutions. This line here is x equal a half, or y equal a half, sorry. And here's y equals sine x. And there's a solution that arc sine gave us. Yes, it is a solution. That is where sine x, or sine theta, equals a half. Definitely. But it doesn't intersect. It's not equal just at that one spot. It's equal all over the place. And you recognize, okay, well, yeah, obviously, sine is periodic. It's periodic with a period of 2 pi. So I can take pi over 6, add 2 pi to that, get 13 pi over 6. I have another solution. I could subtract, get negative 11 pi over 6. I could do that again from that one, get negative 23 pi over 6. Yeah, I've got infinitely many solutions. And yet, even with that, we still only have half of the solutions. We got all these other ones missing. Right? Just recognizing that, okay, we have a solution, and we can add 2k pi to that. Where, in other words, we can add 2 pi to it any number of times. Any integer number of times we want, we'll still have solutions. That's all true. That's all well and good. But that's only half of them. Right? We're missing this one. We're missing this one. We're missing this one. We're missing the other half. And the other half arises because, if you remember from our law of sines escapades, that the sine of the supplement of an angle is equal to the sine of the original angle. So if a solution was 30 degrees, then the supplement of that, or 150 degrees, or 5 pi over 6, is also a solution. So yeah, one half stems from our specific solution we got from arc sine. The other half stems from the symmetry present in the sine function. So 5 pi over 6, and then add 2 pi to that. Add 2 pi in the other direction. Subtract 2 pi more. And that gives us all of our solutions. So if we have some solution, call it theta, then you add 2k pi as many times, or add 2 pi to it any number of times. You've got half the solutions. You find the supplement of that, or negative theta plus pi, or negative theta plus 180 degrees, call it what you will, and that gives you the other half of the solutions. So we would say for this, the general solutions is pi over 6 plus 2k pi, where again 2k pi just denotes the periodicity of sine, and the other half is 5 pi over 6 plus 2k pi. So that was the trick to sine. So let's go to cosine now. And I want you to tell me this, right? Recognizing that pi over 3 is a solution. So let's see, here it goes. Sine goes away, cosine comes up. There's pi over 3. And that gives me a solution. I can add 2 pi over 3 in either direction any number of times, and that gets me half the solutions. But what's the other half? What is our other half? What's the other specific solution we can work with here? So go ahead and stop and think about that, and let me know what you think, and we'll pick up there. And the answer is negative pi over 3. You get negative pi over 3, and you get that because cosine is even. Cosine has the even property. Cosine of negative theta is equal to cosine of theta. So if you have some solution, say pi over 3, then negative pi over 3 also works. So we have pi over 3 plus 2k pi, and then we have negative pi over 3 plus 2k pi, and that together gives us all of the solutions. That's our general solutions there. Of course, we can write that. It's usually also common convention to write everything, all your specific angles to be between 0 and 2 pi. So we have pi over 3 plus 2k pi for our first specific solution, our first half. And our other half, which was negative pi over 3 plus 2k pi, we could also write as 5 pi over 3 plus 2k pi. I mean, for that matter, we could write it as, negative 11 pi over 3, or negative 7 pi over 3. We could write it as anything, and because of that, it's usually convention to go from 0 to 2 pi, be on the unit circle that way. But that's it. That's a way to do it. That's just convention. If you were to instead tell me it's everything coterminal with 60 degrees, and everything coterminal with negative 60 degrees, you would still be correct. That would still be a valid way to represent this solution set. Because you have told me all of the solutions to the equation cosine of theta equals to 1/2. All right, so we're on a roll. So here's the question now. I've got a solution to tangent of theta equaling 1/2, 26.57 degrees. And so I can add 2 pi to that to get half the solutions. But what do I need to use to get the other half? So let me illustrate that here. There's tangent. There's the solution we got, right? 0.464, because we're in radians mode. That's the real value there. And there's 2 pi plus that, 2 pi minus that. I'm still missing half my solutions. What's the other half? What can give me the other half? So tell me that, and we'll reconvene. And yeah, it is actually a fun fact again, right? We have interesting properties. We had the supplement property. I don't know, call it what you want for sine. We had the even property for cosine. And now we have the fact that tangent is periodic with 2 pi, but its actual period is just pi. Right? You add pi to it, you get all the solutions. So the trick there, if you would call it that, is instead of adding 2k pi to get half of it, let's add pi. We'll add k pi and we'll get all of them. So with tangent, you add just pi any number of times and you get all your solutions. And so we would say for this one, recognize we don't have nice solutions, that all the solutions are either 0.4636, give or take, plus k pi, or about 26.57 degrees plus k 180 degrees. And that is all of our solutions. Good stuff. So now we know how to represent our general solutions for sine, cosine, and tangent. So the time has come to return to the question that got us into this mess. Was a solution of sine squared x plus equal 1? And the way you can get that is with pure algebra. You first solve for sine, and you do that by taking the square root of both sides, and that gives you plus or minus 1 after you do that. Fun fact for those of you who have had algebra, the reason why you have to do plus or minus actually stems from the fact that sine squared is always positive, whereas what was inside could have been positive or negative, so you get plus or minus that way. But anyway, you take the square root of both sides, you end up with sine x equal to plus or minus 1, and sine x equals to 1 at pi halves, nowhere else actually, because the supplement of pi halves is pi halves, and sine x equaling negative 1 is true at x equals negative pi halves, or 3 pi over 2, the supplement of which is again negative pi halves. And so we get that pi over 2 plus 2k pi is one set of solutions, 3 pi over 2 plus 2k pi is another set of solutions, and we can actually combine those by the symmetry present to say that all the solutions to sine squared x equaling 1 is x equals pi over 2 plus k pi. And that's because if you add pi to that, you hit 3 pi over 2. You add pi to that, you go up to 5 pi over 2, which is coterminal there. Add pi again, we're back coterminal here. So this is a way to encompass all of our solutions. And we'll work in class going forward with nice ways to sum up our solution sets. And that's a good start, I think. That's a good stopping place for now. Let me know what issues you're having, what's confusing about what we're doing. Is it a matter of finding general solutions? Is it a matter of finding a specific solution and turning that into general solutions? Or is it a matter of dealing with the symmetries or the properties of the individual functions? And let me know what you think, and I will see you in class.